Hi, my name is Takumi Kobayashi. I'm working at National Institute of LSD and University of Tsukuba in Japan. This work addresses multi-level classification. In single-level classification, softmax loss is widely applied with great success, but it is replaced by binary cross entropy loss in the scenario that multiple labels are given to a sample. So we propose a novel loss function to provide good properties of softmax loss to multi-level learning. In addition, we also present a novel two-way formulation to apply the loss for enhancing descriptive power of features from two aspects, class-wise and sample-wise aspects, to improve performance. A real image frequently contains multiple targets. It naturally poses multi-level classification to predict multiple labels in an image beyond the standard single-level approach, such as in ImageNet classification task. The multi-level setting is a natural extension of a single label, but from a viewpoint of learning, the loss function is totally different. In a single-level learning, we have witnessed a great success of softmax loss. On the other hand, in the multi-level setting, it is replaced by binary cross entropy BCE loss. The BCE approach decomposes multiple classes into a bunch of single class classification, in contrast to the softmax loss, which directly deals with multiple classes. So there is a gap between the softmax loss and the multi-level classification. In this work, we propose novel multi-level loss. It consists of two components. First one is a novel loss function, which is derived from softmax loss formulation. So it provides good properties of softmax loss to multi-level learning. For example, it does not need weighting over classes, which is one of the issues in BCE loss. Second component is a novel two-way approach to apply the proposed loss function. We consider sample-wise and class-wise ways for enhancing descriptive power of feature representations. Softmax loss is written in this form by measuring difference between single ground truth logic and the other logics aggregated by a log sum exponential. The term of log sum exponential is a key point in this loss. Here we call the logic of ground truth class as positive logic and those of not annotated classes as negative logics. The log sum exponential function smoothly approximates maximum value in the negative logics. In other words, it makes the loss function focus on the hard negative logics, which are hard to classify. Then let's think about the softmax loss in a multi-level scenario. We can naturally formulate it by the average of single-level softmax losses across positive logics. In each softmax loss, however, the target positive logic conflicts with the other positive ones as if there are negative logics. The conflict positive logic might unfavorably dominate the log sum exponential function. This analysis inspires us to formulate the novel loss function to deal with multiple positive labels more directly. We here divide the whole logics into positive and negative sets. These logic sets are represented by using log sum exponential function respectively. In the negative logics, we can apply the log sum exponential in the same way as single-level softmax loss to extract hard negatives. On the other hand, it is applied to positive logics in a different way. The hard positive logics are related to a minimum of positive logics. In order to approximate the minimum logics, the log sum exponential function is computed over minus sign logic values. As such, we can handle any numbers of positive logics, and the loss tries to discriminate negative and positive sets without considering the comparison among positive logics. So no matter how many positive and negative logics we have, the loss adaptively focuses on the discrimination between hard logics. Then we also propose a novel approach to apply the proposed merge label loss function in a two-way manner. This is a logic matrix drawn from min-merge. The first way is to compute the loss across multiple classes. It is a similar way to the standard softmax loss. By doing this, we can enhance class separation at each sample. Then the second way is to discriminate samples at each class. This is a similar way to BCE loss, which decomposes multiple classes into a bunch of binary classification tasks. The class-wise loss enhances discrimination among samples which belong to different class categories. It may be related to contrastive learning, which also considers discrimination among samples in the self-supervised learning. Note that in both ways, we have to cope with multiple labels and require the proposed merge label loss function. These two types of losses are simply merged into the proposed two-way loss, which enhances discriminative feature learning from those two aspects. This slide shows one of the evaluation studies for ways of computing losses on MS Cocoa image classification task. We measure performance by means of two criteria, which respectively evaluate average precision of predicted multiple labels from the viewpoints of class and sample discriminations. The class-wise and sample-wise losses produce good performance at the corresponding criteria, respectively. And note that they also produce good performance even on mismatched criteria compared to the softmax loss. This is because the proposed merge label loss function effectively uses the multiple positive losses for learning discriminative features through separating hard, negative, and positive losses. The method further improves performance by combining those two-way approaches. The last slide shows that the proposed method produces good performance compared to the BCE-based losses on various datasets by using diverse network models. For the details and other experimental results, please see the paper. Thank you for your attention.